So good morning, everybody. It's 9 o'clock and we're starting our first session of the day. My name is Oksana Smirnova, and the session is on streaming, readout, and data management in different contexts, as you shall see very soon. We will start with a talk given actually by two speakers, Giulio Eulisse and David Rohr, and they will be talking on the O-square software framework and GPU usage in Alice online and offline reconstruction in round 3. So the speakers will be, there will be two speakers giving the same talk, and the questions will be after both of them finish. Thank you. So
I'll make a full screen. So good morning, everyone. It's actually a pleasure to have been invited here, and we are delighted to present to you what we've been doing during the long shutdown in Alice and how that resulted in the current data taking we are doing. As it was said, this talk is actually divided in two parts. In the first one, I will give you an overview of the software framework, and then in the second part, David will go more into the details of the offline and online reconstruction, in particular for what concerns the GPU utilization. In order to understand our new software setup, one has to see what are the changes in Alice for round 3. And probably you know about it, but the detector went a major upgrade during the shutdown. There are new detectors, sub-detectors that have been introduced, and the readout of our largest detector, the TPCs, have been completely redone from scratch. So what happened was that we went from less than 1 kHz triggered events in round 2 to over 50 kHz of continuous readout data, at least for LED data, in round 3. This, because of the way the simulation, the reconstruction actually works, we actually have to reconstruct data in a global way in what we call timeframes of 2.8 milliseconds. The net result of all this is that we have to reconstruct 100 times more events, and that we need to store 100 times more events. However, since we cannot afford storing the raw data as it is, we actually need to use GPUs to compress them online so that the data size becomes manageable. And all this in a flat budget scenario of the WLCG, which means that we have to use all the resources available, and during the time the beam is not there, we want actually to exploit our GPU farm also for the offline data processing. In order to tackle all this, it's how the O-square project was born to address the needs of Alice in round 3, and this is our new computing architecture. What happens is that we get away from the traditional differences between online and offline computing, and we only talk about synchronous and asynchronous phase, synchronous to the beam actually being there. What happens is that you have the data coming from the detector. The readout is performed by the first layer of a first level processor, or FLPs. They assemble, they do the readout, and then there is the network between the first layer and the second layer that assembles these time frames of 2.5 gigabytes in size. And the data is shuffled around the second layer of machines, 350 nodes, each equipped with 8 GPUs. And this goes under the name, each node goes under the name of EPN, Event Processor Node. And after the initial reconstruction of the TPC is done, and the compression allows us to store the data is stored on some SerNet storage. And when the beam is off, we have the synchronous phase that takes over, where we reconstruct with the final calibration. We reconstruct all the detectors that we were not able to reconstruct during the synchronous phase. And the results go to permanent storage. Keep in mind that then analysis only happens on the AOD, the analysis object data. The takeaway message I want you from this slide is that the system is actually homogeneous throughout the whole chain and even beyond in the analysis, although I will not talk about it in this talk. Let's go a little bit into the details of the framework. It's actually a layer design and a collaboration with our colleagues FAIR and GSI, which goes under the name of Alpha, like Alice and FAIR. And the central part of this design is the toolkit that goes under the name of FAIR and Q, which provides our transport layer. Just to give you a general idea of how FairNQ works, the computation happens in the so-called devices, which are separate Unix processes. And this is an actual model design. So you have that multiple devices actually coexist in what we call a topology. And the devices can exchange messages on what is called channels. This already gives you an idea. One of the features of the framework, that is that certain devices can be deemed to be expendable, so that online, for example, you can exclude certain QC tasks if they are failing or if they are not working without actually stopping the data taking. Also, one of the nice features of FairNQ is that if you're running on the same node, it of course optimizes the data passing, which is eliminated completely, because what happens is that the payload are actually stored in shared memory, and the devices only exchange pointers to those payloads. However, this remains a message passing framework, so we are able to actually describe in the same way computations and message passing happen on the same node and across the network. Again, having an homogeneous setup for the whole system. On top of the transport layer, Alice brought its own data model. I will not say much here. I just want to say that it's actually supporting multiple backends. We have Root and Apache Arrow for what concerns the analysis part, and for what concerns the GPU part, we have simplified zero copy layout that is optimized for GPU usage. On top of this, we build our own real framework. It's the so-called data processing layer. And the idea is to hide the hiccups of a distributed system from the user and present a more familiar data flow system. So basically, users define a description of a DAG in terms of tasks and the physics quantities. And then it's up to the DPL translate that into FairNQ topology, injecting extra service devices if needed, and taking care of parallelism and rate limiting. In simple words, what happens pragmatically for the users, there is this data processor specs. You specify the input and the outputs. You provide the algorithm that goes from the inputs to produce the outputs. And there is a few extra features to specify parallelism. And the system, when you specify implicitly the topology this way, for example, you specify for data processor, like in this example, then it's up to the system to produce the final topology. And what the user sees when they run on the laptop is this GUI that you see on the right side, where the topology is actually running. So let me make it a little bit bigger and give you a few details about the GUI itself. You can already see here the 4 FairNQ devices that are actually running. The yellow arrow are the channels between the devices. And the GUI shows the state of the processing. So you see the timeframes in flight, and the different blinking lights represent different states in the processing chain. You can actually click on any of the nodes and you get the logs for it. And of course, that was simple, and just to give you an example, but this is exactly what happens, for example, in a synchronous reconstruction, or at least a simplified version of it that you have here. You can already see a few of the features. So you have in red, circled in red, the GPU processes that then share 2 CPU-based processing chains that are deployed on 2 different NUMA domains by DPL. And this is just to say that this is how we build all our processing topologies. Going back to the DPL features, another important thing is the integration with the control system. So each FairNQ device actually runs a finite state machine, but it then expects an external control system to transition between the states. And this, of course, is a natural way of integrating things with the control room and experiment control system, where the experts can at the pit can start and stop the various runs. However, this is generically implemented, and the DPL, when we are not running at point 2, also substitutes the control system and provides a way for the user to run on the driver on the laptop with in the same way, substituting the control system with what we call the DPL driver process. This is particularly important because this is also what allows us to run on the grid and to do things like the asynchronous reconstruction, which is run from the DPL driver. So this way, as I said, we have a continuous homogeneous system from the readout to the running on the grid. As an extra perk, the GUI that I was showing before was actually running on the laptop using a Metal backend, but we can actually connect to the processes, to the driver via a web interface, and the GUI information is pushed through WebSocket, and you can inspect the workflows when they run on the EPN, for example, via web interface. Going back to other features of the DPL, DPL actually runs in the running state of FairNQ, and it provides the so-called event loop. And the way this works is that by using a Linux feature that is called ePOL or Mac KQ, what happens is that devices are waking up only when there is incoming data on the input channel. And only at that point, if the conditions are satisfied, the user code is actually run. This means that the whole system runs asynchronously, and we have multiple timeframes in flight. And this is what we call horizontal parallelism. Not only that, because of the features of FairNQ, we are also able to look at the same data in parallel from different devices, as long as the dependencies between the tasks are satisfied. So we can also have what we call vertical parallelism. Of course, the first objection that one have when one sees this kind of design is how do we avoid data piling up on the slowest data processor? And in order to solve that, we have a back channel which allows us to implement rate limiting. So basically, we limit the number of in-flight timeframes. And the way it works is that as timeframes process through the chain, they get to the endpoint, which then notifies the first element in the chain that something has been processed. And after we ensure that there is the less than the maximum number of timeframes in flight, we can inject a new one in the system and limit therefore the number of in-flight timeframes. This is currently working with timeframes, but is actually generic. And for example, we can do the same with the available shared memory, like we do for the analysis part of the framework, of the chain. Another problem is that we can have certain devices that are faster than the others. Typical case is the GPU devices, which can process faster than the downstream ones. And what DPL provides is a facility to multiply the given device and have, for example, in this case, one of them take all the even time frames and the other one take all the odd time frames. That said, the one-to-one mapping that I've been showing so far between devices and data processor is not actually mandatory. We actually have a feature that allows us to run them cooperatively if the dependencies allow for that. And this is particularly used for cases like digitization, and we're working to make sure that the feature can be used in a general manner. And talking about the future, another thing that we are looking into is making sure that we can actually integrate the multiplexing and pipelining, and therefore having a sort of multi-threaded streaming execution for thread-safe data processor. And since we are here, I think I now leave the floor to David to explain you more about the. Yes, it's not annoying the mouse.
This is not looking correct. Why does it show multiple slides together? No, but it's not showing it correctly.
They're smaller than the others.
Maybe we should go to 100%. Maybe we should go to the right.
Zoomed in a little hard. Is that super hard? That's the slides are integrated.
Yeah, I think they're a different resolution because can we just use another PDF view or whatever? Then it shows.
It's just
Yeah, just download it and open with anything else.
because you see how that one is, and then you go down, and as you go, that's how it's all uploaded.
No, but look, if we download here, let's just save it there. So we just forward because can we just use another PDF view or whatever? Then it shows.
It's just
Yeah, just download it and open with anything else.
because you see how that one is, and then you go down, and as you go, that's how it's all uploaded.
No, but look, if we download here, let's just save it there. So we just forward. Yeah, sorry for that, apparently. Thanks also from my side to have the opportunity to speak here about GPU usage in Alice. And before I come to really the GPU part, I just want to remind you of the most important aspects of the Alice processing that are important for this talk. So point one is we are not processing events or collisions anymore. We are processing time frames. So we have continuous data, as you see here in the background, of a configurable length. Last year it was 11 milliseconds. This year we went down to 2.8 milliseconds. So this is the data unit we are processing. We are never looking at smaller data. The second point is that we have the synchronous processing, which is basically the online processing. We have two computing farms here, but the majority of the processing happens in what we call the EPN computing farm. So this is what I will be talking today about. Point three is that we have the online processing where we use the GPUs, but since we use the same computing farm also for the offline processing, our goal is of course to use the GPUs in the best possible way also for the offline processing. And then point four in the introduction is a bit what reconstruction steps are we running in online and offline. So at the synchronous, the first thing is detector calibration. The example that you see here is TPC space charge distortion calibration, which is quite compute intense. But the important message here is that it needs tracking, but it needs only 1% of the events, so not much statistics. The second thing we run online is data compression. This we run for all detectors and apparently for all events. And for TPC, we do what we call track model compression, which stores cluster to track residuals instead of full clusters, which reduces the entropy for better compression factor. And for this, apparently, we need 100% of the TPC tracking. And then since we need tracking, we need event reconstruction, also for other things like QC. But besides the TPC, where we need 100% tracking for the compression, 1% is enough. So basically, we're fully dominated by TPC tracking. And this is totally different in the asynchronous processing, because in the asynchronous processing, we basically have 100% for all detectors. So the mixture of the processing steps is totally different compared to online. Okay, then before I start with GPU, let me just remind you that there's a long history actually for GPU usage in IRIs. We started in 2010 in run 1 using 64 consumer GPUs in the high-level trigger. We did the same in run 2. And the change now in run 3 is that we have a much larger farm with more than 2,000 GPUs, and that we start to use GPUs also for asynchronous or offline processing. So what steps of the processing chain are good for us to be offloaded to the GPU? And I will first look at the online part only. So in the synchronous processing, we are totally dominated by TPC because, as I told you before, we only have 1% of the tracks of the other detector. So we are dominated by TPC, and this is more than 99% of the workload. So the canonical thing to do, particularly since we have enough experience with GPU processing on GPUs, is to do the online GPU processing fully on the GPU. And that is what we call the baseline scenario. So the baseline scenario is what was mandatory for us to do data taking, because without that, we would basically not be fast enough to do the data compression, so we couldn't store the data, we couldn't run. But since we want to use the EPN farm also for the asynchronous processing, we are following up what we call the optimistic scenario. And in the optimistic scenario, we want to have better GPU utilization also for offline processing. So which steps are good for the offline processing? Apparently it's more than TPC. And what we decided on is that we do the full central barrel global tracking on the GPU. So you see an illustration here on the right of the detector. So we start from the inside with the inner silicon tracker and then outside the TPC until the time of flight detector. And here you see now basically the processing graph of all the steps that belong to the global barrel, to the central barrel global tracking chain, to be read from the left to the right. And okay, I highlight a bit what is synchronous part and what is asynchronous part and what belongs to the baseline scenario, and which is only the extension of the optimistic scenario. So let's look at the baseline part first. And here you see the steps. We have the color coding for the state of the implementation. So you see for baseline, everything is green, which makes sense since this we are running since 2022, apparently. If I go to the asynchronous chain, including the optimistic scenario components, you see that several components are still red or brown, which means they're still work in progress. Actually, work haven't started yet. So the reason is we were focusing on the baseline to get the synchronous processing running. And now, and in the next year, we will be optimizing the asynchronous processing on the GPU. Okay, with that, I will come a bit to the implementation. And for this slide, I actually decided to just have the bullets here. I have detailed slides in the backup, but I would just have to skip over the slides if I would show it here, so that I don't have time for that. But if you're interested, look at the backup. I will give an overview right now. So the first important point is that we want the GPU code to be modular. So you can think of that again as like a processing graph on the GPU where you have different algorithms and they can run independently or they can run in a chain. And if they run in a chain, we avoid the data transfer from the GPU back to the host and vice versa. So it's not a chain on the GPU. The second point is we don't want to be locked to any vendor. So we do generic C++ coding, and then we just have small wrapper codes that can dispatch to different GPU backends. At the moment, we support CUDA, HIP, and OpenCL, and we can dispatch to OpenMP for the processor. And okay, we try to not use any special features, but we could do with ifdefs. The third point is that we want to deploy a common software on all the processing nodes, independent of whether the node has GPUs or not, and we don't want to have special builds. So the technique we are using is that we always compile all the GPU code. We basically compile the same code multiple times, once per backend, and then each goes into one plugin that is loaded at runtime. And with that, we have a transparent and optional GPU usage. So whatever GPU is available on the node, you can load the corresponding plugin at runtime. If you have two different GPUs, you can even load two plugins, and you can use that transparently. Then we want to minimize the management overhead. So the first thing here is point 4, that we avoid memory allocations during the processing. So we basically allocate huge memory segments at the very beginning, and then we have our own memory allocation, which distributes it at runtime to the algorithms. And the second related point is DMA transfers copying data from host to GPU. So here we have the standard approach to pipeline the processing. So we split the data in chunks. And while we do the processing in GPU kernels on the GPU for one chunk, in the background, we copy the data for the next chunk to the GPU. So that we basically have 100% GPU utilization by kernels, and we never wait for the data. An important aspect here is, of course, that the chunks must be large enough to exploit the full parallelism on the GPU. But in our case, this is more or less guaranteed since we have timeframes with more than 100 collisions. So this is just enough parallelism. And the last point here is actually important and complicated. So we want to have ideally the same output on CPU and GPU, and ideally this would be binarily the same output. But what we learned is that this is not really working binarily. And this is for two reasons. So first we have concurrency, but we have parallel algorithms that might depend on the order of some things, not for physical reasons, but just for technical reasons. And then also there's non-associative floating point arithmetic. So when you do fused multiply add, for instance, result can be different than when you do multiplication then addition. So it's actually, it complicates the algorithms to guarantee fully deterministic, binarily complicated results. Therefore, we say, okay, we want identical results on the QA level, but not on the binary level. Okay. Now coming to the implementation more on the hardware side. So what servers do we use and for what reason? So the idea is we want to have the best cost performance ratio, obviously. And by using multiple GPUs in the same server, we can reduce the overhead of the server cost and of the network cost. And we can also share the GPU at the processors and the memory for multiple GPUs, which gives us synergy effects. There's one thing though, we avoid inter-socket communication. So we have dual socket servers with two CPUs and we try to avoid communication in between. So we basically split the server in two virtual servers running independently with one exception. And that is we have only one network interface card in the server, which is then shared. We also try to avoid inter-GPU communication, and this is quite simple for us. We just do one time frame individually on one GPU, independent from all the other GPUs. And then one GPU is driven by a host process, or the host process could run CPU only. And of course, we can run multiple algorithms on the same GPU. If it's inside the same process, then they can share the memory. And if it's different processes, then okay, then they use disjoint memory allocations. Okay, with that, we decided to go for 8 GPUs in one server, which seems to be a sweet spot also from PCI Express capabilities. We did Monte Carlo simulations, how much memory and how many CPU cores we need to drive these 8 GPUs in an efficient way. And with that, we came up with the server that you see here on the right, which has 8 MI50 AMD GPUs, 64 physical CPU cores, half a terabyte of memory, and HDR100 InfiniBand network. Okay. And the workflow we are running, this is basically what Giulio showed to you before. It's this DPL graph of the workflow to be read from the left to the right again. And we can highlight the two NUMA domains. So you see it as basically no communication inter-socket, except for this input, which goes to interleaved memory because there's one interleaved process that is then read by both of the chains. And you can also see the two GPU parts, one per NUMA domain with 4 GPUs and 4 processes each to the GPU part. And okay, I just want to mention this is a simplified version of the workflow. It doesn't contain all the detectors. It didn't contain QC and calibration. The full workflow is this, but here it's difficult to see anything. It's just to give you an impression of the complexity what is running. Okay, now coming to the performance, and I will talk about synchronous performance first. So this plot was actually shown at last chap already. What we added right now is the MI100 GPU performance on top, which wasn't there last year. The bottom line is that one of the MI50 GPUs that we have at the moment replaces 80 processor cores in synchronous processing. In asynchronous, it's a bit less, it's only 55. And the reason is that the synchronous is not fully tuned to the CPU because we don't run it there. But okay, the bottom line is basically we would need more than 2,000 servers with 64 cores each to have the same compute capacity, and that would be prohibitively expensive, so we couldn't do that. And the improvement of the MI100 over the MI50 is 35% faster. And so what is the experience from online running last year? We can say it worked smoothly. So PP processing and also the LED test in October was no problem, but it was also not high rate. So the real challenge will actually come with 50 kilohertz LED, and we didn't have that yet. We will have it October this year. What we did, of course, is Monte Carlo simulations to see that we are ready for that. And this looks okay so far. And yeah, at the moment we have an EPN farm that consists of 280 servers, but as we are speaking, we are extending this farm to 350 servers because we want to increase the margin basically that we have. And the new servers will have MI100s instead of MI50s. Okay, with that, I will come to the asynchronous reconstruction. So as I said, synchronous is quite simple. We have 99% TPC. That is the baseline scenario. That is on the GPU. That's it. There's nothing to be done. In the asynchronous, it's more complicated. So if you look at the right plot here, we have the baseline processing in green, which is 60% of the processing. If we go to this optimistic scenario, we have the additional yellow parts, then we would go to 80% of the processing that we could offload to the GPU. So now the question is, what kind of speed up could we expect with that? First, let's think what is the speed of light. And the speed of light means we have 85% of the compute power of the server in the GPU measured using TPC reconstruction. So if we reduce the CPU wall time or CPU time by 85%, that's the maximum we can do, otherwise we would be GPU bound, then we could get a speed up of 6.5. That's the absolute maximum we can get. Today, we can offload 60%, so reduce the CPU time by 60%, which gives us a speed up of 2.5x. And in this optimistic scenario, when we will hopefully be able to offload 80%, the speed up should go up to 5x when we have the full tracking for all the barrel detectors on the GPU. Okay, before I give you the real measured numbers, I just want to highlight 2 points. So the first is that we were really struggling with the scheduling in the asynchronous processing. And the point here is that synchronous and asynchronous are totally different. In synchronous, we have 350 timeframes per second. Each of them is 2.8 milliseconds. So it's really smooth injection of timeframes to the processing chain that just comes from the data taking. I mean, it's given to us, and we just have to keep up with the rate. And of course, we want to have processing margin to handle fluctuations and whatever. But for asynchronous, it's different. We basically want to have full CPU utilization. We don't want to have any margin. We want to use 100% of the processing power. And we can basically decide ourselves how fast we inject the timeframes in the chain. But of course, we have to make sure that we do not run out of memory. And the problem is, if we use only this timeframe rate limiting that was introduced by Giulio, we basically don't have a smooth injection rate. We can basically inject a lot of timeframes, then we hit the limit, then we have to wait until the first reach the end, and then we inject again. So we have bunches of timeframes that are injected together and then nothing for a while. And this doesn't give us a smooth horizontal and vertical parallelization over this processing graph. We have always localized hotspots in the processing. And if we do that, on the right side, you see the CPU load over the processing of 5,000 timeframes, I think. And you see it's not smooth, it goes up and down, and it really goes down to below 50%. So what we did is we have some heuristics that does some time measurements, and then we basically smoothen out the processing rate. And with that, we get to the CPU load that you see in this plot. We have 11% higher throughput by just changing the injection rate and smoothing that out. And we reach 90% CPU utilization. And then you have to consider the 10% that are not used as basically hyper-threaded cores. So this is basically zero loss in compute power. Okay. Then second point is, I think it's trivial, but I think it should be mentioned. How do we do the processing? So we don't do synchronous and asynchronous on the same node. We split the nodes in 2 scheduling pools, and then one goes to synchronous processing, one to asynchronous, and we can move the nodes between the pools. All the nodes that are not needed at the moment, they will go to the asynchronous pool. And then if nodes are needed for synchronous processing, we move them, ideally with some lead time so we can finish the processing that is currently running. But okay, if needed immediately, then we just kill the jobs and move them immediately. Okay, so for the measured performance, I have 4 cases here. So 2 cases are CPU only. This was basically done to have a comparison. What is the speed up with GPUs on the EPN servers compared to CPU only? And then I tried to have 8 cores used in one workflow, and then we can run 16 of the workflows in parallel, or vice versa. We could have 8 16-core jobs basically on the. That's basically like the granularity of the scheduling that you do in the Slurm. And then we can do similarly for the GPU. So one case is we split the EPN in 2, so having 2 NUMA domains that would be identical to what we do in the synchronous processing, or we can also split the EPN server in 8, and then each of the parts would have one GPU. And then below you see the processing time in all of the configurations. So you see the time if we run only one instance, or the time if we scale it to the full server by basically running multiple of the chains in parallel to have full load. And with that, we see that the improvement of the GPU over the CPU in the fastest configuration is 2.5x. So that's exactly what we expected from the 60% that we offload. So we see it all comes together, it makes sense, and we also have full CPU utilization. And okay, naturally with that, the configuration we are running on the EPN server is this one NUMA domain configuration with 4 GPUs per workflow. Okay, before I conclude, let me just talk to you about some lessons that we learned. So first is GPUs can speed up the processing significantly, but I think we were quite lucky because we had this hotspot with the TPC processing, which makes it simple. So as we also now see for the asynchronous processing, it gets more complicated when you have a more heterogeneous compute load. What we also learned is that inexperienced users can easily contribute to existing processing steps and change the algorithms, but it gets more difficult when you really want to implement completely new processing steps. For this, I think you need really an expert. Then the debug GUI that Giulio and I have shown was really useful to inspect the things on the fly, and it's good to have access to that remotely when it's running online. So it's quite useful tool. We learned that scheduling for synchronous and asynchronous is quite different, and that we had to do some work to make the asynchronous work efficiently. And we also learned that at some point it's good to optimize a bit for memory and lose small fractions of efficiency somewhere, because it just makes the things easier to handle. That is the reason why we went from 11 milliseconds timeframes down to 2.8 milliseconds now. I think a very important point is the usage of this common software framework that can go to multiple GPU backends. So we can basically switch the vendor by just using a different backend. And this is also really valuable because it finds bugs. And you can have failures that appear on one GPU, but not on the other. And with this, you just see more errors, and then you can fix them before they will hurt you. Similarly, we also support multiple Linux distributions and macOS, for instance, and also this is helpful because you just see different behavior and you fix it on all of them, and this makes your infrastructure more stable. Important, I think, is also to have this default build that contains all the GPU backends, because then you don't have to work with individual builds. You just have one distribution which just works everywhere. And I think one important thing is also in run 2, we had one monolithic process that had everything. And this was a bit failure prone and difficult to debug. But the idea to do everything in individual processes is also a bit complicated, because then you have too many processes, too many context switches, and you need too much memory. So a good compromise in the middle is needed. Okay, then let me conclude. Alice has 99% of the synchronous reconstruction on the GPU. And for practical purposes, I think we can say we have the full reconstruction on the GPU. It doesn't make sense to port the remaining percent. For the asynchronous processing, we are at 60% on GPU at the moment for the 650 kilohertz PP data of last year. And this will hopefully go to 80% when we finish this optimistic scenario. The experience from the synchronous processing is that so far it was working nicely, but we are really looking towards the October of this year when we will have the 50 kilohertz of that, because that is the real challenge. And for the asynchronous processing, we have started the 2022 processing on the EPN farm using GPUs. And at the moment, we have the speed up of 2.5 that I've shown. So that, thanks for the attention.
So now it's time for questions. Please raise your hand there.
Hi, thanks for the detailed description. So this is Attila Krasnodar from CERN. I have many questions, but just to focus on a couple of curiosities. So do you know off the top of your head how long your GPU kernels take on average? So what's the order of magnitude that when you launch a kernel, how long it would take, or how many kernels you have to launch per second, as we heard earlier from CMS, that in CMS and Atlas, we launch a lot of kernels.
So for one time frame, I think it's in the order of 2,000 kernels, and the runtime of the kernels is between a millisecond and a second.
Oh, okay.
So we have really long kernels. For instance, we have a long track fit where we just do fit of 2 million tracks in parallel. So that is really long running, but then we also have short kernels. So it's really versatile. Okay.
And the other thing I was wondering about, so you run multiple processes per GPU, right? So multiple processes need to talk to a single GPU at the same time. That was not entirely clear.
We could do that, but at the moment we only run one host process that drives the GPU. We could share the GPU, but we're not doing this because it's more efficient to have one host process.
Makes sense, because I was going to ask you exactly how you set up the sharing between the processes. Okay, thanks.
There's another question.
Hi, David Giulio, thanks for the talk. Andrea Bocci from CERN. I'm curious about one of the statements in the previous slides where you say that running a single monolithic application has robustness issues and is harder to debug. Could you elaborate on that?
So one example is everything is multi-threaded in the same process. So one detector writes out of bounds somewhere, it doesn't crash immediately, it kills the processing of another detector half an hour later. That takes quite a while to debug.
Okay, fair enough. Thanks.
think we're a bit pressed for, there is one last one.
Hey, Lindsay Gray for Emulab. Hi, everyone. Just a weird question on user experience of getting everything so much onto the GPU. How much coordination between development teams was there to get all the data formats sorted out? Or was it mostly just a small group of enthusiasts doing this?
Okay, I mean, what we have running on the GPU right now is two detectors. So it's
Okay.
TPC data format.
But there, even there, there's a series of detectors
TPC
or a
data
series of
format
formats.
was defined by me, and I do the TPC code, so that was simple.
Okay, small group of enthusiasts. Yeah. All right. Thank you.
Okay, but thank you, everybody. And let's thank the speakers again. And our next speaker will be David Lawrence talking about streaming readout and remote compute.
Well, I am David Lawrence. I'm from Jefferson Lab. I'm the lead for the experimental physics software computing infrastructure group there, where we do a number of things that are related to the experimental physics program that we run. And I'm going to talk today about streaming readout and remote compute. So I'll probably be preaching to the choir a little bit here, but I'm going to start off with trying to motivate why it is that we actually run streaming readout to start with. So you can imagine that if you have a very simple system where you put a detector in next to your accelerator and it's just a single scintillator and you're going to take data with that, you can write out everything that comes out of that detector straight to your storage, and it's going to be proportional to the luminosity of your experiment. If you double your beam current, you're going to get double the data rate, the first order in your detector, and you're only going to really be limited by the network bandwidth and the storage bandwidth that you can use for this. So that's all well and good, but we of course don't have really small single detectors. We have large complicated detectors that are made up of multiple parts, and they start producing a lot of data that is starts to run into that storage and bandwidth limit pretty quickly. So the way that we have gotten around this historically is that we will take multiple detectors, the fast ones at least, and we'll combine them together into some kind of coincidence, and we'll look for that coincidence, and that will cut down the rate. Of course, there's I don't know if you can see the mouse on here. I should probably use a feature for that, but you can see that there's some portion that's correlated, and there's where your physics is going to lie when you have something in both detectors that are coming from the same reaction, but you'll also get some accidental rate that'll go like your luminosity squared. And the goal of the triggering system here is to try to make that beta as small as possible, so you're getting rid of the things that you don't want to keep while keeping all the stuff that you do want to keep. Of course, that's not the end of the story. We have other subdetectors in there, so as you're writing out all of these things to storage, your additional detector will have a hit rate that is proportional to the luminosity, and you will have a trigger that's proportional to other detectors, and you will end up with terms in here that go all the way up to the luminosity cubed. The luminosity, the first term here, that has the gamma in front of it, is the one that you're most interested in most of the time, because that has your real physics in there. But this other stuff you've got to suppress, and the way that we do that in the future, because you're always going to lose out if you don't have a 0 in front of those higher order luminosity terms, is to have a more complicated trigger. And so it gets to the point where you can't realistically do that just in hardware, especially when you have slow detectors, where the readout time of the detector for a particular event will necessarily contain many different events in there, thinking of things like drift chambers and such. So to try to suppress this, we have really complex triggers that we will put into the filtering scheme in our streaming readout. So we have to grab, in a nutshell, we want to continuously read out the entire detector. So you have access to all of the data of the detector at one time, not just a portion of it. You can then filter the data based on a holistic view of what the detector is seeing. In order to do this, though, you need to more or less continuously calibrate your detector in real time, which you may not have had to do the entire detector before in triggered concept. And then, of course, you have to do some reconstruction of data in real time. And all this is a very big challenge. So the old system would only use some small portion of your detector and have front-end electronics that were tightly coupled to the trigger system. You were then limited somewhat on what readout decisions were made, and certain biases in your trigger were introduced because of this. And you would also have to have some complex triggering system that included support for back pressure in case you were unable to read out everything because your triggers were firing too fast. In a streaming system, though, we will have much more compute put onto this. Calibration will be done, reconstruction will be done. And because we're already having to do this at such a high level, it only makes sense to try to extend this to do the full reconstruction at the time you're taking the data, which will help reduce the time to analysis. So you'll end up having come off of your detector, instead of writing it to storage and then spending the next several months trying to calibrate and replay the data, you'll just have it immediately available to start your physics analysis, which is a great thing. This also makes the whole system very seamless with what was determined offline before versus online. These things now kind of merge together a lot more into one complete system. So there's already a number of these things in production. You've probably heard of the Allen system at LHCb. They have some nice documentation here, and I have the link to it. I've seen this picture shown here even at this conference. This one I stole from a slide from back in the streaming readout workshop in 2021. But the nice thing about this is it just shows how all of the detectors up front have massive network connections, putting 32 terabits per second off of your detector to a massive GPU farm that then reduces it down by a factor of 30 and does basically the full reconstruction right away. We just heard about the very nice O squared system at Alice, and I think this is a bit of an older slide, but it's still got the right orders of magnitude on there, where they do something very similar, process all of the data up front with a massive farm so that we can take the data off of the detectors and make decisions based on holistic view of what's going on. Of course, there's plenty of talks here at CHEP, and some of these have already happened, but the slides are available, and I would encourage you to go look to those for more information. There's a couple of other places that are also using streaming systems that are a little bit different. The SPhoenix experiment over at Brookhaven is using what they call a hybrid system. They're reading off from their TPC a large amount of data into the compute world, and but they still have a hardware trigger that is flagging timestamps, and those flagged timestamps can then be used to figure out which timestamps to record in your data from your fully streamed information. By having the data, though, read off of the detector, you also have the opportunity for what they would call opportunistic events, so they can pull some additional events that are done from not a hardware trigger, but from a software trigger that can be applied to the portion of the data that is fully streamed. Right. There's another one that's actually really interesting if you haven't heard of it. I've seen some references to this. There's the TRIDUS system. This is the second incarnation of the TRIDUS system for the cubic kilometer neutrino telescope. This is a large detector that is under the Mediterranean Sea, where it has lots of PMTs that are trying to look for light that is produced from neutrino interactions. But they have a very different motivation for streaming than what I presented before. In this scenario, you don't really have access to a lot of equipment that's down under the water. So if you have a lot of fancy electronics that's down under the sea and something breaks, it's a little hard to get to and to fix it. So they put this all data to shore concept in, where all the data is transferred out of there to the shore, to the compute facility, and they stream it that way. They get about 40 gigabytes or gigabits per second on average. But of course, they have to be prepared for the very large event that may come in from some very energetic neutrinos. So they have a capacity that's up to 3 times as much as that. And they also have an additional 20 gigabits per second coming from some acoustic detectors that are down on there. But I'll move on to the next part, which is how do you really handle this? A lot of people in here are probably familiar with the WLCG. This is a concentric system of compute resources where the LHC is at the middle. It produces the data. It has a large amount of the processing of the data. And as we've seen and heard a lot here, including in the previous talk, there's a lot of the compute resources are being focused more into the center of this because they have to process the data immediately as it comes off of this detector, but then it gets distributed out to the other layers, moving away from there. So that is a concept that has worked very well for the LHC, but there is another idea that I'm going to put forward here that is being considered for the EIC, which is called this butterfly model. And in this case, instead of trying to focus as much computing power as you can right at the site of the experiment, we want to really embrace the distributed computing aspect. And so at this, in this kind of model, you would have the EIC as a detector at echelon 0 that's centered here at Brookhaven National Lab. The SDCC is their compute center. Jefferson Lab is a partner lab in the experiment. And you would stream this data out from the detector to other sites. You just need to worry about getting it down to a small enough stream that can fit, but that doesn't have to be too difficult of a task if you're clever about it. This automatically gives us 2 copies of the data. And moreover, we can rely on either compute's capability that is at those national labs or other sites that are outside of those national labs to distribute the compute or to use that compute resource by distributing the data to it and then pulling the results back and then having these the results available for final analysis from the storage that's supplied by these national labs. So yeah, so the difference here being that these other sites are set up to handle and provide compute resource for lots of different areas of science, not necessarily just in nuclear or particle physics. So we get to the economy of scale, so to say, from those sites that already exist for lots of other reasons. Now, one thing that's necessary to make this work is the network bandwidth. I think everybody's probably heard of Moore's law. Some people may have heard of Nielsen's law. Nielsen's law is basically the same thing, but it's showing that the network bandwidth on your high-end network connections basically goes up by about 50% per year as you move forward. And so that means that if you had something like a Brookhaven ESNet bandwidth that has a couple of 200 gigabit per second connections to the ESNet network going out of the lab, if we were to run the EIC today, which has an estimate of 100 gigabits per second of data production coming off the detector, it would take about 25% of the total bandwidth to do this. But of course, this experiment is not running today. This experiment is running in 10 years. So by that time, you could expect that the network bandwidth is going to grow by almost a factor of 60, and which means that we would have should have plenty of bandwidth. Of course, the marketplace provides this. We don't have to drive the technology to increase the bandwidth. It's already being driven by a lot of factors outside of particle physics. So we ride that wave. So if we had really 100 gigabits per second, we'd only be using 0.5% of what their total offsite bandwidth was. Even if we're off by a factor of 10, and we need to do a terabit per second offsite from Brookhaven, that's only going to be something like 5% of their bandwidth, which should not be too difficult for a major experiment like the EIC. So things to keep in mind, though, that network upgrades must be motivated by requirements, even if the technology exists because of industrial pressures. It doesn't necessarily mean that the lab is going to upgrade just because of that. There has to be reasons, so we have to give the motivation. And they also tend to happen in very big steps. We don't have big upgrades to bandwidth from these DOE sites or lab sites every year. So we have to kind of plan for this. And if they need some long or large implementation like laying new cables or fiber, then of course you may have a long lead time for that. So planning is very essential in doing this, but there should be really no reason that we couldn't really focus and embrace this distributed system. So once you start thinking about distributing your compute outside, you may start thinking about how you could integrate into your detector the networking and the compute, even though they're far apart geometrically or geographically, into a common system. And this is one of the goals of this so-called EdgeFAT system, the ESNet JLab FPGA Accelerated Transport project. And on this one, we would want, the goal is to take data from our experiment and to stream it out through a system that has a very smart traffic shaper at your remote site that is coupled directly with the compute resource at that site. Yeah, so I'll give that in a little bit maybe easier to understand terms. So we have, say, a streaming system over here on the left, and it's producing time slices, and each detector system has produces its own set of time slices. The time slices are colored here in blue, green, and red, and the detectors are in the shapes in the circles, triangles, and squares. It sends them in and it tags this information in metadata on the packets that are sent out over the network. It goes to your remote compute facility, and you have this load balancer, which is a fast FPGA with its own high-speed network connections, and it will rewrite the headers on these packets to redirect the location of where they should be going to based on some steering system that's in strong communication with the host. And what that ends up doing, what that ends up doing is making all of the time slices from all the times, each detector for the same time slice show up on the same node. So it's integrated into the networking system automatically to make sure that all of the pieces that you need for that particular time slice show up at the same place. At the same time, this is going to be smart enough, since it's in contact with the host compute system, to be able to elastically allocate or free up nodes as needed. So as your stream comes in, if it needs more compute nodes, it will allocate them from the larger system, or it will free them up. And you can even incorporate some AI steering into this, which may be smart enough to detect which host is going to have some free time coming up soon and make sure that the next set of data goes to that particular host. There was a nice talk on this that's going to be tomorrow. That'll give you a lot more details that you would, if you want to go there and learn more about it. All right. There's also a couple of tools that we have been working on to try to support this on both other ends. The IRSAP system environment for real-time streaming and acquisition and processing. This has mixed language support, so you can have algorithms that are written in different languages, but it can all talk to each other very seamlessly because it's a loosely coupled system. It's separated into 3 different layers. There's an orchestration layer at the top. You have your actor layer here and a transport or communication layer down at the bottom. And so this was the thing that would be able to take the data from your front-end electronics after you've done some initial filtering from your data acquisition. It will run it through some other algorithms to try to reduce the size more. These are algorithms that could be part of your normal offline reconstruction, and it would attach the appropriate headers to it that would work with the EdgeFAT system as it sent the packets out. Another end of this would be the Giraffe system, this JLab integrated research infrastructure across facilities project. This focuses on workflow co-location and interference detection. And what this would do, one of the primary things this would do is if you're really thinking of a distributed system in which you may have multiple remote sites that are capable of handling your stream, this would be able to talk to those. And if you have one site that suddenly has less capacity, then and you need to reduce it, then that could switch over and hot roll over into another compute facility and redirect your streams over there. And so it would have minimal user interaction with this, and you would never drop data on the floor, which is always the biggest worry when you're using a streaming system, is you don't want to spill data to the floor. There's other talks on this. One of them already happened. One of them is tomorrow on the IRSAP system, so you can find more information at those. And the last thing I want to go into is the data quality monitoring. Because if you're doing a streaming system, any type of data acquisition, you need to have good data quality monitoring. But I can't help but put in here the plug that we want to do more with AI on this, because there's so much data coming in, so many different things to monitor. It's kind of impossible for humans to look at everything. And so there was a very nice system from CMS that they did with their electromagnetic calorimeter, where they used these images of histograms. This was an example where there's one section was out. They pass it through a trained autoencoder that produces the image, and then they can take the difference of that output and put a threshold on to identify sections where there are problems and have the AI kind of alert people immediately for this kind of anomaly detection. There's also the Hydra system that we've been working on at JLab. This one also is looking at things where it's easy to see in the image. It's an image class or image computer vision system where it looks at the same images a human would look at, but instead the AI makes a decision on whether there's a problem or not. Subtle things can be easily identified by the AI. And there's even this very nice experimental feature called with the GradCam integration, because what you want to know if you're a human told that there is a problem with this plot, you want to know where the problem is. And the GradCam can focus you on that by overlaying onto it. This is what the AI thinks is the problem with this plot. So explainability is a big thing on this particular. So I will point to another talk that already happened yesterday, but there are available. And we're at the end, fortunately, timing is perfect. Summary and outlook. So streaming readout is motivated by the need for higher luminosity, particularly when you're looking for rare reactions. Also, if you're just trying to look for finer binning to get more feature out of existing reactions that we already have measurements on. We have multiple experiments that are already using this in various forms. There is an online, offline blurring that's going on necessarily because of this, and it was really highlighted in the previous talk. The availability of the high bandwidth, high reliability networks will allow for near real-time utilization of compute resources far from the experiment in the future. And that is probably the thing I want to underline the most, is that we want to try to move to a system, certainly wherever we can, that we distribute out these streaming experiments to places that we don't have to supply large compute resources right at the experiment necessarily in order to take advantage of streaming technologies. And of course, multi-architecture compute resources are expected to play large roles in this, as they already are, particularly for AI ML. And I don't have time for my final thoughts, so that will remain a mystery.
Yeah, thank you. So time for some questions. Can even ask what was the final thought?
I will say I predicted there would be no questions because I was so clear, but.
Oh, there is a hand there.
What are your final thoughts?
My final thought, I'm going to make you come up and ask me after the thing. So anybody who wants to know my final thought, I'm going to keep it mysterious rather than spoil it and have people disappointed in it. Good.
Hi, excuse me, Gordon from University of Washington. Great talk. I love watching this project move forward. You talked about the this real trend for the streaming experiments getting into a place where you don't have to collate the computing resources, which is great. But I'm just trying to go through the logistics in my head. So, for example, if you're streaming data from EIC to JLab, JLab can't suddenly decide to upgrade their routers while the experiment is on. I mean, I'm just starting to think of like all of these connections. And I was wondering, as you all are putting together these plans, how far have you gone in thinking about these small little things that could potentially cause huge hiccups?
Well, I think the bandwidth that's needed for the EIC is certainly not that large that we'll be able to handle that easily at JLab. So that particular thing, there's still a lot of, you're right, there's a lot of details that have to be worked out. There's nothing that's so far that looks like it's on a scale that would cause a great concern. So I think those are details we think we can work out pretty easily over the next few years. But it is important, planning is important because the details could creep up on you. It's a good point.
So some of the arguments that you make are built on the validity of Nielsen's law. Now we know that Moore's law breaks down at some point. when does Nielsen's law break down?
Yeah, that is a good question. And, my response to that would be that Moore's law will break down for different reasons than Nielsen's law will break down. And Nielsen's law, you can actually get a lot more out of just parallelizing your network connections. Whereas Moore's law kind of broke down because of, power concerns and, the size you can make transistors, all these other things that kind of play into, you can't keep building up this concentrated compute source, but networks are more spread out. I can always add in more fibers and build my network that way. So I'm not as concerned with that breaking down as I was in Moore's law. That's a good question.
All right, I think actually, okay.
I've
this
had
very
my
last
hand
question.
raised for a while, so, okay. Yeah, what I wonder is, you're basically doing your event building in the wide area network, in a very similar way that in the older experiments, we would do that with a big network switch, but the big honking network switch is a device that you have complete control over, and it's real-time capable and reliable in that way, that I kind of have my doubts about the wide area network. And so to gain confidence in this, I would be doing all kinds of smaller prototypes to scale up to that. And I wonder if you feel the same way, and if that's your plan to in the next 10 years to try that.
I fear nothing.
Okay,
But,
that's great.
I will say that this is why we're partnering with ESNet, who are real experts on this. And we're also doing testing right now with NERSC, where we're trying to drive data from JLab all the way to the other side of the country to a large compute resource so that we can try testing this exactly as you're saying. So I fear nothing because I put a lot of planning in ahead of that. We don't try to turn the switch on tomorrow without having checked that all the pieces are going to work together at scale. But I appreciate your point very much.
Right, no, I think we're pressed for time, so other questions probably can come in the break. So let's have a round of applause for our fearless speaker. So the next talk will be by Wouter Deconinck, talking on slightly different aspect of data management, which is data management in nuclear physics, cultural changes for larger collaborations. There.
Not on the screen yet. Oh, there it is. Okay, great. Thank you. So yeah, I'm going to take it in a little bit of a different direction here, talking about cultural change, in particular in nuclear physics. So I'm going to talk about the nuclear physics in the CHAP acronym. The topic is going to go over two areas, talking about what changed in the nuclear physics environment, and we went over that just in the past talk already about streaming readout. And this is going to focus not just on the electron-ion collider, but it's going to look forward, of course, to the electron-ion collider. I'm going to justify this also with some current experiments that are ongoing, like BlueX, some of the items that David has talked about as well, S-Phoenix doing streaming readout. And then I'm going to go into how this is different from nuclear physics as it has been done in at least this part of the world most recently, and what that means for the culture that has to change in this field. So figure this one out. Oh, down. Okay. So electron-ion collider, you've seen this slide before in several talks, I imagine. So this is going to be the first major collider to be built in North America in the 21st century. Polarized electrons, unpolarized protons, light ions, and unpolarized heavy nuclei. A variable center of mass energy, so that makes it a little bit different from for example, the LHC. But in particular, it will be a high luminosity, up to 1,000 times more than at HERA, the previous electron-proton collider. It's going to be an international facility, intentionally international, which is slightly different from many of the past nuclear physics experiments. It has already a large user community of about 1,200 users in many different countries and institutions. And the three key questions that the electron-ion collider is aiming to answer is about what is the mass, where does the mass of the nucleon come from, where does the spin of the nucleon come from, and what is happening in terms of the the emergent properties in dense systems of gluons. So this really points to the difference between looking at a nucleon as a set of 3 valence quarks and then looking at what is actually happening inside the gluon fields there. So over the past, let's say, nearly 10 years, we've gone through a lot of work in building community around the software aspects of the Electron Ion Collider through first the EIC Software Consortium as part of a generic R&D program, then moving into the EIC user group and the software working group there, and now as part of the EPIC detector collaboration, which is the main project detector collaboration at the EIC. So there's one detector as part of the project. There's the hope that there will be a second detector on the accelerator as well. Throughout this process, the focus has been on community building, on building interoperability, building common interfaces, having people talk to each other to avoid the kind of fragmentation that is typical in some of the nuclear physics community. This is also moving forward into the development of the EIC, and I just mentioned there's going to be a second detector. So even while we are in this one detector collaboration, the EPIC collaboration, we are looking at the second detector and developing our software practices and computing practices with the aim of that being able to be adopted by the second detector effort as well. So again, to point out the differences from other nuclear physics experiments, we are, with the Electron Ion Collider, going to be located at one site, but crucially different. There's going to be 2 equal partner host labs, Brookhaven National Lab and Jefferson Lab, instead of typically one lab. It's intentionally a very international community, an international facility where there will be international contributions, which is also somewhat different from current nuclear physics experiments. And we're mirroring some of the structures on the CERN model. For example, there's a resource review board, and we already see a demand from international partners to contribute with in-kind computing resources, which sort of naturally pushes us towards the distributed computing model. I'm not going to say that we're going to replicate the WLCG, but as David pointed out, we have some ideas about how this distributed computing model will look. This is not exactly new for the Electron Ion Collider, but all of these components together are new for the Electron Ion Collider. So, for example, GlueX has already been using distributed computing resources at the Open Science Grid. Other experiments have done that as well. SPhoenix is doing streaming readout. That's also something that has already been done, but it's taken to a new level. It will be taken to a new level at the EIC. Streaming readout is, of course, a big change, as was just pointed out. In addition, we also want rapid turnaround to results. So all of that is different from how nuclear physics has been doing this in the past. So just to point out the computing model. So this is a butterfly model for distributed computing. In part, that comes, this model has wings. There's 2 wings associated with each of the host labs. And there's a good reason for that, because many of the university sites have connections with one of the 2 host labs already. And so it makes sense to structure it around that existing model, so that we don't force people to change their affiliations with host laboratories. The other part that this model includes is sort of a natural way of extending to international partners. So in this echelon 2, where the large computing facilities are, that's where other sites can easily plug into. For example, international sites. For example, also HPC sites, which would then, for example, allow us to scale in the way that we use AI/ML as part of this interface. So all of this requires some changes. So let me now talk a little bit more about the cultural aspect. So culture is defined, or sort of in organizational psychology, typically described as the way we do things around here. And how we are doing things around here in nuclear physics is different from what we're planning for the EIC. So we have to sort of make this change. There's going to be more larger, more complex software computing systems, these distributed systems that we have to start using. We won't be able to, and this doesn't just extend to computing and software, but also to detectors. So it's not going to be able, we're not going to be able to look at nuclear physics in the EIC as sort of the, it's like high energy physics, but you can still understand everything, which is sometimes something we say. It's also going to require that to conquer this complexity, that we adhere to more modern organizational practices. So code reviews, working together with Git, sharing code more readily, which is not something that's in the culture of nuclear physics as much as it is in high energy physics. We also are going to have to keep in mind that there are different users that are coming in either as new users, for example, students who don't have a preconceived notion of what nuclear physics is like and how it's supposed to be done, and then professors or senior scientists who have some ideas of how it should be done and who are probably going to need to be more of a focus on this culture change. Now, to understand how culture will have to change and how we can best achieve that change management, we have to understand our communities. So that's where we come into the topic of user-centered design. So we have to study our user community to understand how to adapt to what that user community wants and how to focus on supporting that user community to the new demands of the electron ion collider. So for example, I just mentioned the two classes of users already. We essentially have the long-term researchers who built their career around nuclear physics, around in some cases, of course, also computing, and who are typically too busy to spend a whole lot of time on reorienting their career and the tools that they're focused on. Short-term researchers, on the other hand, students who are coming in who have short-term career goals, who are typically thinking in timescales of 3, 4, 5 years from now and building a portfolio to the next step of their career, they're going to be focused much more on, or they're going to be drawn to learning things that are going to be useful for that next step of their career. So they're going to look at what are the current computing models that are of interest to industry, that are of interest in other experiments, in other communities, for example, from the point of view of nuclear physics. So that's going to help us understand in what way we can encourage that community to be productive in our environment. So as part of user-centered design, we are studying our user community. We're doing an annual state of EIC software survey, which allows us to compare from year to year how our efforts are actually having an impact. We see this longitudinal impact. We have focus groups where we can really drill down into some of the themes that are coming back for each of those different groups of users. So some example of questions that we ask here related to event generators, detector simulations. Other aspects there are questions about programming languages, where are people doing their computing and things like that. That then turns into these focus groups, which we turn into personas or archetypes, as Marcus discussed in the plenary on Monday, but also in user profiles that are actually associated with names. The archetypes are anonymous, they're artificial constructs. User profiles are actually people. They're relatable. We can see what the individual users are struggling with specifically in the software, what tools they're using specifically in their day-to-day environment, and what their expectations are, for example, for the next step of their career. That has led us into the development of these software principles, statement of software principles, which extends to computing more generally as well. There's 8 software principles. They're listed there in their full text, but I've sort of summarized them in a single word as well. So we want computing for the EIC that is diverse, integrative, heterogeneous, that's user-centered, that's accessible, that's reproducible, that's collaborative, and that's agile. So all of these are sort of the adjectives that we're going for with these statements of software principles based on the input from user-centered design. We have sort of a mental model that goes with that as well, and how user-centered design really informs other aspects of the entire computing, software, data management aspects of the EIC. So from user-centered design, all of our efforts there, we sort of inform discoverable software. What is it that people want out of their software? How are they best going to be interacting with that software, learning that software as they go along? User-centered design also informs how we support certain workflows. From those workflows, we can then build template repositories of template workflows. That informs our choices for workflow management systems. And then together with workflows and discoverable software, that helps us then implement our data analysis preservation strategy for the experiment. So all of that sort of follows from user-centered design. If we do the things that users are naturally going to want to do or feel drawn to, and we understand their incentives for doing certain things, then we can steer that in the direction of what is productive for the experiment. Most of this, Most of this is new to nuclear physics. Everything from user-centered design, from sort of a central approach to workflows, workflow management systems. Until now, most of this is fairly fragmented from one experiment to one experiment to one experiment. There's no real community-supported efforts that have gotten wide traction in the nuclear physics community as they have in the HEP community. So in our efforts based on user-centered design, we've selected a single software stack, which includes a number of community-supported software components. So we have Gian4, of course, EDM for HEP, and Pod.io as a data model that sort of is a glue between all of the different interfaces. And then we have components like Jana2, and we're building on approaches like GitHub and GitLab, which are also, again, not necessarily as new in HEP, but are somewhat less common in, at least at the scale that we're using them in nuclear physics. For geometry description, we're using DD for HEP. So it's one key example of a community-supported experiment agnostic project that is really a resource to the high energy physics and to the nuclear physics community now in the context of EIC. Similarly, Pod.io is developed in this same way. EDM for HEP is developed in the same way. And so what we're really hoping for is, as part of EIC, when we're developing our own tools, that we sort of have a way of giving back to this community as well, and developing aspects of our computer environment that is able to be adopted by other components. In particular, again, looking at the second detector, we are not going to develop something only for one detector, but we want it to be used for the second detector. So that's one of the reasons why inherently we're developing things in the same community support model. So I already went over the GitHub and GitLab aspects, which is fairly common in high energy physics. So I'm not going to spend too much time on that. So our key in selecting components for our software stack is informed by user-centered design, and it brings us to this experiment agnostic community software. So you'll see these components come back in Key for HEP, or from Key for HEP. You'll see us adopt likely things like the Phoenix event display, the HSF conditions database, reference implementation. So community supported components that are shown to have a broader reach, that are going to be able to get our younger short-term researchers to learn something that's going to be useful for the next step of their career. And of course, this isn't just limited to the high energy physics community. We're also using components or looking at components from the wider HPC community like SPAC, or components from the data management community in Russia. So of course, thanks to all of the contributors, of which many of you are here, because we definitely appreciate all the efforts, and we're of course aiming to become contributors to that as well. Now, again, this all challenges somewhat the model of nuclear physics, where in the past everyone's been developing their own software, and sometimes this leads to a little bit of a cultural adaptation that has to happen. So, for example, we have some misunderstanding sometimes from users that don't necessarily understand that DD4HEP is not something that was written for EIC. It wasn't, clearly. But we are using it, and many nuclear physicists are coming to this and think that, well, it's the software that we're using, it must be written just for this one experiment, because that's the way it's always been in nuclear physics experiments. We also have sometimes some struggles with conveying this to especially funding agencies, that there's some who have a tendency to associate some external risk to components that are not controlled by the project itself. So this leads to a little bit of a challenge sometimes in conveying that there's a benefit to using these community-supported projects as opposed to developing everything from scratch, even though when you develop everything from scratch, you sort of have 100% control of what is going on there, and you can fire the people if they don't get the work done. So as some key examples of how in some of these community-supported projects are really integrating the community, and then other experiments in this are I'm just going to put up 2 slides here from ACTS and from SPAC, which is really doing a great job of integrating the broader community. And so one of the examples here is how ACTS structures its its weekly developer meetings, which has been a great way to integrate the community, and is a very accessible community. And so we're certainly looking at that as one way of structuring, or community supported or community projects as well, to be welcoming to other users. And for example, SPAC has a similar approach with a very open development culture that allows outside communities to really participate in. And so we're looking at that as ways to structure or practices as well. So applied to distributed infrastructure, distributed computing, we're sort of taking the same track, right? So we're looking at what are industry perhaps standard approaches that we can adopt over homegrown code. So for example, it's much more likely that we're going to use approaches that are standard interfaces like XRuT and S3, rather than developing something ourselves. And we're already actually using S3, as some others have talked about at the conference already. And the other approach that is important here, just like we're using a modular approach to the software stack, we're going to focus on a modular approach to the distributed computing infrastructure and to the computing infrastructure in general. Again, that allows individual users to make innovations in individual components without having to understand the entire system as it works together. Now, these are two areas in particular, distributed computing, where we're going to be talking about that and making some decisions on the specific components that we're going to pick over the next year, again with input of the users in a conscious, intentional decision-making process. So in summary, I hope I've convinced you that the EIC is really bringing nuclear physics in a different era of streaming readout, which will require distributed computing. And that will be a way for us to integrate all of the international components in a seamless way as part of the computing strategy. Now, this requires a change of some of the practices in nuclear physics. And so we've been using user-centered design as a framework to inspect what the users have as expectations, and that's informing our software choices, our computing choices, and in particular, it's driving us towards these community-supported software frameworks that allows our users to have a broadly applicable skill set, in particular those short-term researchers. Thank you.
Thank you. So, questions to the speaker, Andy here.
Andy Salzburger, CERN. Father, many thanks for this. I think also inspiring talk to some extent. My question is, how do you get those? I like the idea with having the interaction to the communities by surveys, but you always get in the surveys the people who are already active, that are already engaging. So did you think about how to include the ones that are not so engaging, to even lower the bar? I know it's very difficult, but
yeah, so yes, selection bias, survivorship bias is definitely an issue there. Selection bias, we're actively seeking out, in particular through those focus groups. We're trying to actively involve in those focus groups people who are not the usual suspects. We are reaching out in those focus groups to people who are not spending 100% of their time on software already. We're moving this explicitly in almost the opposite direction and trying to figure out, okay, you're someone, you really don't like doing software. Can you tell us why you don't like doing software? And what is it that we are doing wrong that makes you not like software? It's not like, why don't you like me? But it's how can we change our practices to feel like you're being more included? So the focus groups there are definitely the key area, because yes, those are not the people who are going to necessarily fill out the survey with same level of zeal as someone who has their own software project that they're trying to sell.
Wouter, great talk, thanks. It's Graham Stewart from CERN here. I think there are two things that are particularly praiseworthy about the way you've approached it. First is the actually laying out the software principles, so it was very clear to everybody on what basis you're making decisions. And secondly, your engagement outside of the nuclear physics community with the HEP Software Foundation, IRI-ABA, EPR&D has been really fantastic. And thank you very much for all the contributions that you've given back to those projects as well, because they're not insignificant. Following on a bit from Andy's question though, I think it is really important engaging with the breadth of the users that we're attempting to serve. And I think historically, we've always had the idea that we should do this, but I'm not sure that we were ever very good at it, you know. And did you learn from like soft sciences like sociology, how to approach this problem, how to phrase questions in a way that users can really express what their needs are rather than what they think the solution could be? Because as physicists, we're very bad at that A/B type of thinking. So how do you make that the most profitable way of interacting with users that can really feed back into the software design and interfaces?
Yeah, in many cases, it's a matter of asking question after question after question, not being happy with the first answer. So you keep asking the why after every answer that the user gives, right? So you know, why do you want this solution? Well, and then you're really starting to hear why they actually want that, and you know, what is the thing they're struggling with. It's also sometimes a matter of not necessarily asking the questions in a way that invite solutions, but asking the questions in a way that is much more general. Like, you know, describe your workflow, describe what it is that you're doing. What is it that takes up the most time? So somewhat more, dare I say, objective answers that are then a good starting point for them to really drill it down. Again, that's also where, for example, focus groups are going to benefit from moderators, from facilitators who are sort of familiar with that approach and can ask those questions and really understand the motivation behind drilling down rather than being happy with the solution focused answers.
Two last questions.
Yes.
Here.
Senevettestein, CERN, thank you for the great talk. I was wondering a bit about the externality risk you were mentioning about the funding, and I mean, particularly regarding the somewhat controversial history of colliders in the US. And this also relates to Graham's question, has that really affected how you interact with external collaborators, particularly outside of your community?
It's gotten us to consider when we are adopting, for example, a choice in a particular software project, it's really had us thinking much more strongly about ensuring that there's definitely a clear contribution from our side, so that we are being, you know, not necessarily seen by the entire community as key contributors, but at least as having an influence on the discussion in those projects. So you know, and this is easier for some projects than others, right? You shall not name any projects that are maybe not as easy to contribute to, but there are some projects where it's easier to have the influence on the development process. So DD4HEP, Quad.io, EDF4HEP are the ones that we, of course, you know, are using, but we have that good rapport with the developers, where if there are issues, we can have good discussions with them, where the projects to some extent have even gone out of their way to change meeting times to be open to EIC time zones and so on. So having that influence on the project and being able to tell our project management teams that, look, they're actually changing their practices to support us. So this is not, you know, it's not just a matter of they're going to drop us as a customer or as a user. That is helpful. And that's, again, easier for some projects than others.
The very last question over there.
Okay, Nick Smith from Fermilab. I really appreciated your talk, and I really enjoyed the messaging about software culture that you introduced here, especially different profiles. There's one profile I think you didn't mention, which is you, the software architect, right? That's another, you know, piece in the puzzle. Can you comment on training pipelines and, you know, career development for that profile?
Sure. And I'm not going to claim I'm the software architect or a software architect. This is all a matter of many different people in the IC, and I'm probably only a minor part in that. But in terms of training, well, there's HSF training is of course one key component at the introductory level. One aspect that I think as a community we're probably struggling with is bridging the gap from sort of where HSF training working group leaves off at the sort of basic, maybe half intermediate level, and then really bringing people up to the level where they're maintainers or core developers in projects. One thing we've found is that these kind of collaborative software development practices, code reviews, assigning people to really review other people's work, even though they're like, and why are you asking me? Is a good way to get them to think of software projects as something that they have shared ownership over. And that brings them into a role of first reviewer, then brings them up to the level of contributor, and then developer. So I think Daniel Katz has some great work on that, talking about sustainability and software development projects and sort of what the steps are that users are going through. It's not something that, by the nature of the duration of the EIC project as it is right now, we haven't been doing this for very long, so we haven't had as much progression of people through the ranks. But we are, for example, trying to instill that approach also by choosing younger people as, for example, conveners of task forces, so that we can sort of give them that boost in their career where they are being seen as doing important work for software, and then sort of using that as a springboard to additional positions of responsibility in software projects.
Okay, let's thank the speaker again. And this brings us to a shorter break. So we're back in 10 minutes or so.
I guess we should start. My name is Randy Sobey. I'm from the University of Victoria. I'll be chairing or moderating this session for the Planning for the Future. We have 3 talks. The first one is by Daniel Elvira on the future of HEP software and computing, the Snowmass report.
Good morning, everybody. My name is Daniel, as I was introduced. And I am a scientist at Fermilab, senior scientist at Fermilab, and I'm also a member of the CMS collaboration. And I have served as a convener for the Snowmass Computational Frontier. The organizers asked me to give a summary report on our final write-up. And I will do that on behalf of my co-conveners and everybody who participated in the process. So I will start with a few words about how we organize the computational frontier within the Snowmass process, and then have a discussion about the newly established and emerging technologies, such as hardware evolution, artificial intelligence, and quantum computing. Then I will quickly go to the findings and recommendations, including the main recommendation that we have, which is the establishment of a coordinating panel on software and computing. Then I will put the report in the global context by giving an outline of the European strategy, and I will conclude my presentation with final thoughts. So I, as a computational frontier convener, I actually took over Oli Gushe in September 2021, immediately after the COVID pause. My co-conveners are Steve Gottlieb from Indiana University and Ben Nachman from LVNL. And I want to tell you that most of the material that you will see here in this presentation is available in the Snowmass webpage. And there's a link here. We organized the frontier in topical groups, and we used a mixed characterization by software and computing topics and also by technologies. And this recognizes the fact that technologies have an immense impact in energy physics these days. That's why we had two groups, one on quantum computing and another one on machine learning. And in addition, of course, we have the topical groups that follow software and computing topics, such as, for example, experimental algorithm parallelization, theory calculations and simulation, machine learning, storage and process resource access, and reinterpretation and long-term preservation of data and code. So we actually gave cross-frontier communication a lot of importance, and that's the reason why we appointed liaisons with both the physics and the enabling frontiers, as well as community engagement. In the interest of time, I will not say too much about the many preparatory events that we actually organized as part of the process. I will just tell you that at the end of 2022, we delivered the future of HEP software and computing, which is the title of our final report, and it was published in the archive. Let's now move to the newly established and emerging technologies and start with the hardware evolution. And I will not actually introduce the CHEP audience to the several computing laws that you are familiar with, but I will just tell you that we have reminded in the report our colleagues in energy physics that we are facing a paradigm-changing computing architecture. We live in a brave new world of computing, and the reason is the breakdown of Dennett scaling and Moore's law. And this has actually generated this evolution of hardware towards heterogeneous systems with multi-core machines using coprocessors, and of course, also complex memory configurations. In the meantime, artificial intelligence has evolved from an emerging technology to mainstream. And although we have all heard about multivariate analysis since the 1990s, and I remember my times in T0 experiment at the Tevatron when this all started, machine learning, modern machine learning was absent from the 2013 report, and nowadays it's making paradigm shifting contributions to HEP. So of course, as you all know, it has really a big place. So most of the machine learning research is actually happening these days within industry, but energy physics require dedicated solutions, and the reason is that we are making very precise measurements and calculations. We need to understand uncertainties very well and do validation of our Monte Carlos, interpretation of our data in the light of our theories, and that requires dedicated tools. And I will not bother you with the examples of algorithms that are popular within energy physics because we've heard a lot about this. I will only say that of course we have the need of specialized software and hardware, and that's the reason why energy physics should be and is contributing directly to the most popular machine learning platforms. And it's also important to guarantee access to GPU resources, not only for prototyping, but also for deployment of our production level software in HPCs. And as you all know, allocation process is kind of a sociological issue, and it has to be amenable in the future to R&D and HEP schedules. It's also very important to do work on recruitment, training and retention of this person power that is so specialized and expensive. And also, it's very important to foster cross-disciplinary collaborations, including industry. And we know that there are challenges with respect to this collaboration with industry that need to be addressed. Quantum computing is an emerging technology that I would say that more than a paradigm shift could produce a revolution. And we know that the problem with quantum computing is the environmental noise affecting the quantum state, producing quantum decoherence. And we are living now through the near-term noisy intermediate scale quantum era that is called NISQ. And in this era, we see rapid development of software for quantum computers. And we are also working within the HEP community in benchmark examples. And once again, the participation of HEP in quantum computing development is very important because we not only need to develop motivational examples, but also we have to make sure that quantum computing evolve in order to be useful for HEP applications, in order to address our needs. And therefore, the field should prepare for the possibility that fault tolerance is achieved by the next Snowmass process in about a decade. This is the post-noisy era. Bottom line is that computing in HEP is not business as usual anymore. That's what we transmit in the report. It is more globalized than ever, so the efforts must be coordinated with partners. The complexity of experimental and observational instruments and the size of the data volume is demanding more computing power, more data storage, and computationally expensive algorithms. And we know that budgets are not expected to grow. The context is flat budgets, so we have to do a lot of R&D. One thing that I would like to highlight is the fact that software and computing in HEP has become an integral part of the measurement instrument. I would claim that computing is not anymore a service, or it's not only a service, but it's an element of our scientific apparatus in HEP experiments and surveys. That means computing is part of the detector, computing is part of the telescope. And another important element to highlight is that the complexity and the physics content, and in particular the impact that computing has in the physics programs, in the physics results, is commensurable with that of detectors, and this is not always recognized. We need to exploit more effectively the synergy between detector and software design. We are very used to utilize simulation to design detectors, but we have to put more effort in actually optimizing parameters of detectors in the future for not only achieving best physics results, but also best computing performance. So hardware evolution calls for a redesign of the computing model for HEP. So we need to work on experimental software frameworks that are nowadays supporting heterogeneous resources locally and remotely. We need to revisit the data management model. And what takes a lot of time is the adaptation and reengineering of almost every piece of software. And that includes the software, the common software tools, such as, for example, event generators, detector simulation toolkits, and user analysis, reconstruction algorithms. And we need to learn how to use portability tools to avoid to rewrite software each time that a corporation comes up with a new piece of hardware. And all of that while we build our computing and software infrastructure for AI, ML. So what we see is a departure of the stability of the past when we just had to sit and wait until the same old software would become faster and the computers would become cheaper. Some of our colleagues in high energy physics still believe that this is the case, and we have to correct this this idea. And for this, we need to invest in research because we need to bridge the needed versus available resource gap. And we don't have to forget about development because R&D is fun, but eventually, if successful, we need to invest the effort in order to take that idea into a production level product. And this is heavy in labor. Person power is rare and expensive. Okay, let's go now to the findings and recommendations, which, as I said, includes a coordinating panel on software and computing. But before that, I would like to share with you a few notes about the computational frontier. And I will highlight, because I don't have too much time, only two of the distinctive features of computing. One is that computing technology and software paradigms change on a much faster scale than the Snowmass frequency and the life of most experiments and surveys. And the other one is that software and computing efforts are neither funded nor managed as projects, and like facilities and experimental devices were typically coordination areas. And this actually is transitioning us very naturally to the first and main recommendation. We recommend the creation of a standing coordinating panel for software and computing under the auspices of DPF, mirroring the panel for advanced detectors, or CPAD, established in 2012. And of course, during the next few months, we will spend a lot of time discussing what this panel will be, what is the charge. But in the report, we tried to describe a little bit the role, and I would like to read it to you. Promote, coordinate, and assist the HEP community on software and computing, working with scientific collaborations, grassroots organizations, institutes and centers, community leaders and funding agencies on the evolving HEP software and computing needs of experimental, observational, and theoretical aspects of the HEP programs. The scope should include research, development, maintenance, and user support. And there is also a recommendation for the CPSC to set up a study group on DEI in HEP computing. And it's also important to say what this panel would not be. It would not be a center, it would not be an institute, and it would not be handling a budget. In addition to this main recommendation, we have identified 4 key areas of need where increased investments would significantly enhance the physics output of our community. And the first finding has to do with the fact that long-term development, maintenance, and user support of essential software packages that cut across project or discipline boundaries are largely unsupported. There is a lot of investment on R&D, but typically there is not a lot of effort put on modernization, maintenance, and user support of existing tools. And there are many examples, among them the many event generators like the experiments use, and also simulation tools such as Jam4. So the recommendation is that the US HEP community take a leading role in long-term development, maintenance, and user support of essential software packages with targeted investment. The second finding is related to the fact that research and development for software and computing that cuts across project or discipline boundaries receive insufficient support. And examples are software and computing for theoretical calculations and generators, cosmological accelerator and detector modeling, machine learning methodology, etc., etc. And the recommendation is that through existing, reshape, and expanded programs, R&D efforts cutting across project or discipline boundaries are supported from proof of concept to prototype and to production. I want to emphasize these last two words because typically we stop in R&D, and when the R&D is successful, we need to invest in developing the tools and deploy it. And here I would like to stop for a couple of seconds and remind you, just in case there is confusion, that the first recommendation has to do with the modernization, maintenance, and support of existing tools, while the second one has to do with R&D. And the third finding is related to the fact that the scarcity of personnel and expertise is jeopardizing the full and optimal use of heterogeneous and high-performance computing resources. And you know that typically software is written for a single computing platform, and nowadays it is really very difficult to make things portable, to take advantage of the diversity of hardware accelerators and resources that are becoming available to us. The recommendation is therefore to support computing professionals and researchers and physicists to conduct code re-engineering and adaptation to enable the use of the heterogeneous computing resources effectively. Let's go now to the fourth finding. Investment in training and career path within HEP for software and computing researchers is insufficient. We need to grow efforts for documentation and training at multiple levels. And our young people know too well that faculty and staff positions for physicists with expertise on software and computing are very scarce, and we are facing an endemic person power shortfall. Therefore, the recommendation is strong investment in career development for HEP software and computing researchers to ensure future success. Let's now put the computational frontier report in the global context, and I'm going to do this by sharing with you some of the key points on computing from the European Strategy Report. They wrote a book, the physics briefing book, and unsurprisingly, the two regions, the recommendations resonate with each other. And the R&D programs are very similar, except for the way they both write the word program. Computing challenges are immediate and need to be addressed now through a vigorous R&D program. It's also interesting to highlight that the European strategy also identified the need for a more holistic approach to detector design, which includes the impact on computing resources, which is something that I mentioned before. There is also the need to strengthen collaborative structures, and also the need to develop human resources, to develop expertise, to recruit, to train, to retain these people with the expertise. And also related to this fact, it's important that computing development activities are recognized as fundamental research areas bearing a large impact on the final physics results. Typically, instrumentation physicists have more success than those of us who work on computing to transmit this message. So let me give you a couple of examples of European initiatives to address these challenges, although you have heard about these initiatives during the last couple of days. So one example is the European Open Science Cloud. That is a cloud for research data in Europe, allowing seamless access to data and interoperable services. The other one is ESCAPE, that seeks to develop common infrastructure solutions for particle physics and astronomy facilities, also push the state of the art in data management and computing R&D, and address common challenges on data preservation, sustainability, and open access to data. And this takes me to my final thoughts. I believe that the Snowmass process was successful, and it was a participative, open, and transparent experience. We, the conveners, hope that the report represents the community faithfully. We hope that all of you feel the same way. Computing plays a fundamental role in the execution of current and future theoretical, experimental, and observational programs. And I would like to state again the fact that I believe that is not only a service, but an element of the scientific apparatus, part of our experiments and our telescopes. Modern computing architectures, newly established and emerging technologies are changing the way we do physics these days, but they also bring transitional challenges, and we have to pay attention to them. We have to be able to achieve a balance and timely support for software from prototype all the way to deployment, not only prototyping. We need to put a lot of emphasis on education, training, career paths in an inclusive, diverse, and welcoming environment. And we need to strike a balance between R&D and the improvement and maintenance of existing tools. And the simulation area is an example of an area that is underfunded. And last but not least, we hope that the coordinating panel plays a role in achieving a coordinated, timely, balanced, effective, sustainable investments in software and computing for HEP. And I can tell you that at the moment, the DPF leadership has decided to establish a task force with broad community participation, with the idea to write a report that they will deliver to DPF with a proposed CPSC creation process. Thank you very much.
Questions? Questions? Let's see. Any hands?
You all feel represented by the report.
They're all happy. Oh, there is one. Oh, way at the back.
Thank you very much. How tightly defined are these various components for software support and development? So for example, you rightly highlighted the potential for quantum computing early on, but there's nothing later about quantum computing explicitly. So is there enough flexibility that say if in 5 years we have fault tolerant quantum computers, we can pivot and use those?
Well, I think that the report emphasizing striking a balance between investments in emerging technologies, well-established technologies, development and deployment of tools that are necessary immediately for experiments, theoretical models also. It's very difficult to say what's going to happen with quantum computing. There are people who believe that within the next 10 years, it will be possible to apply to high energy physics applications. There are a few examples in our report and even in these slides. But once again, the idea is to strike a balance on investment. And of course, we would hope that these technologies are available as soon as possible. I don't know if I have answered your question.
Hi, thanks for the really nice talk. I just have a quick question about how, I guess I also am not really super familiar with how funding works, but one thing that I've observed as a student is that it seems like a lot of, I guess students who do stuff where it's computer science tools in service of analysis is usually more strongly rewarded than students. And I guess this also applies to postdocs and PIs who focus on the R&D stuff with databases and things that don't directly serve, I guess a physics analysis and a physics result. And I was wondering if that plays into how these various aspects of computing and software are funded.
Okay, I'm not sure I understood the question. You are saying that because there's a lot of people, I have to say.
This might be a bit American centric, I'm not sure. But it's
You are saying that there are many aspects related to software development, and one of them is physics analysis, but maybe you are highlighting the importance of R&D or software development.
Yeah, exactly. And I was just wondering whether the priorities of how different aspects of computing and software are funded differently.
Well, I think that when we say that we want to recruit and train physicists and computing professionals to work on software computing for high energy physics, what we mean is that they are trained on the many different modern skills, tools, technologies that are necessary to put together the computing for the experiment. Analysis is an area that is very important. If you take a look at what people are doing on analysis facilities and analysis tools, and we had a couple of presentations on the topic, it's very important, and you really need very well-developed skills in order to develop those tools. Regarding doing physical analysis, I consider that to be part of the physics activity, and I think every physicist has to have the basic, software skills in order to, analyze, his or her data. Is that what you're?
Sorry, could I let me rephrase the question. What I mean is that I think for students, we're typically trained towards software for analysis, but not software in the other aspects of in your case, you're presenting about quantum computing and the various distributed systems, stuff like this. I think it's very specialized knowledge that I don't think is as easily accessible. And I was just wondering if there's efforts towards training up people in that front and funding that type of development. We could talk afterwards.
We both
Sorry.
agree that it's hard to hear with all the reverberation, right?
Maybe get in contact after.
Yeah, we can
that might
talk
be the
after.
easiest to deal with that. Anyway, I think we need to move on. The schedule is tight. Thank you. Let's thank our speaker again.
Thank you very much.
The next speaker is Haiyan Gao, who will give us a report on the nuclear science long-range plan and computing. Okay. Is Haiyan Gao, who will give us a report on the nuclear science long-range plan and computing. Okay. Yeah, the arrows, or there's also this.
Okay. Okay. Good morning. I'm Haiyan Gao from Nuclear and Particle Physics Directorate at Brookhaven National Lab, and also from Duke University. So my talk is not really to give you a report, because the nuclear science long-range plan is still an ongoing process. But what I would like to do in this talk is just to give you a status update on where things are, and also tell you a little bit about some of the computing related aspect in the long-range planning. And I have too many slides, so in the not to risk not thanking people who helped, so I wanted to put my acknowledgement slide first. And I also would like to thank David Dean and also Marcus Tyler did a very nice job on Monday already, so which make my job easy. Okay, so as I said, a lot of people needed to be thanked for. So let me just tell you a little bit about nuclear physics long-range plan. Our field started long-range plan actually in the late 1970s. So the first nuclear science advisory committee was formed appointed by DOE, US Department of Energy and National Science Foundation in 1977. And the first long-range plan report came out in 1979. And it was actually kind of amusing when you look at the people who participated at the meeting to discuss about the long-range plan for the field. So there were about 30 people. And the town meetings we held last fall for the current long-range plan, that included about 1,300 people. And so that kind of tell you that the community is more engaged and also more inclusive in the process planning for the future of the community. And the current long-range plan, we call 2023 long-range plan, and that started last summer. So the committee received the charge from DOE and NSF last July. And as typically what has been happening is that this is a community-driven exercise. And typically American Physical Society of the Division of Nuclear Physics has been responsible for organizing the town hall meetings. And our field is a little bit different in the sense that we organize through three science-focused town hall meetings, and many important areas such as detectors, such as computing, are all closely integrated into these town meetings. So there were 3 town meetings, and the first one was hot and cold QCD last fall, and then followed by the nuclear structure, reactions, and astrophysics last November at Argonne, and fundamental symmetries, neutrons, neutrinos, and short name is FSNN, and that happened last December. And I ordered my talk, actually not exactly in the chronicle order of the town meetings, but rather I start with the nuclear structure reaction and astrophysics, and in Argonne. It was very, very well attended by people and many participated online. And this field really are addressing some of the most fundamental questions in nuclear physics and in physics in general. So just, I'm not going to read over all the questions here, but let me just read out a few. For example, what is the nature of nuclear physics that binds protons and neutrons into stable nuclei and rare isotopes? And how do the rich phenomena of nuclear structure and the reaction emerge? And what are the limits of nuclear existence? And what features arise near and beyond those limits? And then there is also the question, how do stars evolve? And what nuclear signatures do they leave behind? And also the nature of neutron star and dense matter. And to answer these questions, the program really involved, you have to have theory and experiment work in concert. And from the experimental side, the facilities, the newest facility is called FRIP, which is the facility for rare isotope beams. And then there is also a facility called ATLAS, and this is not the ATLAS at LHC. And this is the ATLAS, which is argon, tandem LINAC accelerator system ATLAS. And then there is also the IRONA, which is the Association for Research at University Nuclear Accelerator, which is a collection of university facilities. And very importantly, theoretical theorists. And in order to arrive at the predictive understanding of atomic nuclei and their decays and reactions, you really need a theoretical theory calculation validated by the experimental measurement. So it's a very close collaboration. And this field, not only, as I mentioned, in order to address these fundamental questions, it also has a very important application to benefit the society. And another very important aspect of this field is that it allows us to leverage the properties of nuclei in order to enable precision test of nature's fundamental symmetry for standard model test and new physics. So the community presented from the computing aspect for nuclear structure reaction and astrophysics that high performance computing at the X scale is very important for some of the important predictive capabilities, such as nuclear matrix element, which is important not only for this field and also for neutrinos double beta decay experiment, and nuclear structure reaction and light nuclei. And you have heard a lot about the IRI-ML. And in terms of theoretical calculation, what is important is the uncertainty quantification, and that is important. And in terms of experimental aspect, and you incorporate that in the detector design and particle identification, as well as particle beam tuning. And quantum computing is another very important great tool, which allows us, particularly is ideal for many body calculation. And this has been going on, in the field. And they are some of the very famous, well-known classical issue in nuclear physics, and quantum computing has a great potential to help solve those problems. And so then, what it needs, right? So it needs the kind of increased access to the capacity, like high performance computing, and also the kind of collaboration and development and support, optimizing code, etc. Okay, so one example, as I mentioned, FRIP is the newest accelerator coming online for nuclear physics. So there are specific challenges associated from the computing aspect. So here's a list, and some of them you also have heard early in the previous talk, and issues like compatibility with legacy software, and also the kind of ability to read out data in triggerless mode, and the ability to analyze data at a much higher incoming rate compared with what has been done, and also taking advantage of the development in AI-ML, for example. So now I want to go to the next town hall meeting report, which is just tell you a little bit about what came out of that town meeting, which is the fundamental symmetry neutrons and neutrino town meeting. And there is a white paper. Every town meeting has a white paper there on the archive. So the kind of research portfolio in fundamental symmetry and neutrino, you can actually think about using this graph and also 3 major categories. So this particular graph is in terms of the sensitivity to new physics in terms of the increasing energy or mass scale. And the horizontal axis is about the decreasing coupling strengths when you think about the new particle you want to look for. And specifically in terms of the search, we're talking about rare and standard model forbidden processes such as neutrinoless double beta decay and particle EDM search and neutron, anti-neutron oscillations, so on and so forth. And the second category is precision test. And these are the kind of standard model allowed process. And you do very precise measurement, then you look for the deviation from the standard model prediction, such as mu on G minus 2 and parity violating electron scattering or hadronic parity violating experiment. And the third category has to do with search for light and weakly coupling coupled particles, such as dark photon, dark particle search and axion search. And in terms of connecting to the fundamental physics or new physics and standard model test, and we are really looking at, the origin, understanding the origin of the neutrino mass, understanding baryon number symmetry of the universe, and understand the nature of dark matter, and also asking the question, are there new forces and weaker than the weak force? So these 3 category of experiment which really allow you to connect all these fundamental questions, and they are color coded here. So when it comes to computing, I just wanted to give you an example. So one of the experiment called Project 8, and it is an experiment to measure neutrino mass using cyclotron radiation emission spectroscopy. So what are we talking about? So in this case, you have to recall the IF radio frequency time series at 100 megabyte per second per receiver. So that translates into 3 petabyte per year. And currently you are looking at 1 receiver and short runs. And but in the future, what the experiment will be looking at is 60 receivers and very much longer runs. So then you will be looking at 200 petabyte per year and millions of CPU hours. And so now this information is a few years old, but I was told that nothing really has changed. So it still represent what the experiment will need. And in terms of challenging for fundamental symmetry neutrino-neutron experiment, so these are very exposure limited kind of sensitivity. So the data is very precious. So you have to keep all the data on disk. And you also want to allow people to have a remote access. And most of these groups do not use a massive parallelism, at least at the present time. And also these groups are not associated with a major facility. And then in the event, if there is a beyond standard model signal and everybody would like to calculate. And so there's also that aspect as well. And another important aspect has to do with lattice QCD calculation. So here I just want to show you a compilation from the flavor lattice averaging group, FLAG 2021, in terms of the isovector actual charge and scalar and tensor charge. And so you can see that lattice has been doing these calculations very, very precisely, and also plays a very important role in fundamental symmetry. So the most tightest constraint on right-handed beyond standard model current came from the combination of neutron decay and lattice QCD calculation. Okay, so now let me tell you a little bit about the first town hall meeting, but I'm talking about it at the end. This is the hot and cold QCD town hall meeting, took place last September at MIT. So hot QCD is just essentially we're talking about relativistic heavy ion collision. So what people are doing is to recreate the early universe in the laboratory and to free quark-gluon plasma so that you actually produce the kind of state of matter called quark-gluon plasma, which, like microsecond after the Big Bang. And then what you wanted to do is you want to understand, characterize the property and of the quark gluon plasma from the first principle of the theory, which is quantum chromodynamics. And so what people have discovered is that this quark gluon plasma behaves like a perfect fluid at RIC as well as at the LHC. So in terms of the probe, one use soft, and which measure the anisotropy and correlation, fluctuation, and you can use the hard jet heavy flavor, as well as electromagnetic photon dilepton probes. And experiment we're talking about are at RIC and LHC, and also in the future FAIR, CMB experiment at FAIR. And co-QCD is also called hadronic physics. Essentially, we are talking about, the property structure of the hadron. So the kind of question people like to ask is, what is the origin of the mass of the nucleon, and what is the origin of the origin of the nucleon spin? And very interesting question recently, physicists are fascinated and working on do gravitational form factors inform us about the origin of the mass, and can they be extracted from measurement? And so there are a lot of very, very interesting questions, and also the question, what is the spectrum and structure of conventional as well as exotic hadron? Exotic means QCD allowed them to exist, but experimentally so far we have not seen them yet. And currently the major QCD facilities in the US, Jefferson Lab, which I hope you know, and many of you have visited. And another facility is located at BNL, which is the RIC facility. And you have heard at this conference already, the future is the electron ion collider for the QCD as the next QCD frontier. And this came out the 2015 long range plan of NSAC. And we recommend a high energy, high luminosity polarized electron ion collider as the highest priority for new facility construction following the completion of FRIP. And FRIP started operation last spring. Okay, so before we move on to the EIC construction, we have a remaining mission to accomplish, which is S-Phoenix. And you also have heard S-Phoenix, and this was also recommended, highlighted in the 2015 long-range plan, is really to understand how this structureless perfect fluid emerged from the underlying interaction of quark and gluons. And as we speak, S-Phoenix has been installed as of last Monday, and we are near the end to get the final approval process at Brookhaven National Lab so that we can start the commissioning of the detector. A very important part is computing, and I agree, computing is a very important part of any experiment. And so before EIC reached the full luminosity, S-Phoenix really represent the most serious demand when it comes to data and storage and computing. And here I have two pictures to show you the new data center at Brookhaven and National Lab, the energy efficient cooling system, as well as S-Phoenix tape library. So speaking about S-Phoenix computing evolution, so this chart shows you both in terms of the disk requirement for S-Phoenix as a function of time. And I should mention that the RIC round 23, we started cool down this Monday, and we will run this year, and then next year and 25 we will finish, and then EIC construction will start. So, and in terms of tape, you can also see the kind of need, and we will be looking at a factor of 4 to 6 increase in the next 3 years. And there's also the computing, which you can also see the blue curve, and the vertical axis on the left-hand side give you the scale for the CPU need. And I'm running out of time, so that I just want to mention that as you have heard, for S-Phoenix, we have a hybrid of the trigger and the streaming readout. And maybe the important thing, just one message here is that the data will be written to tape. At the same time, we have the reconstruction on disk, and that typically takes we have 2 weeks of time to do that, and allow us to do the first and second pass tracking, as well as particle flow jet reconstruction, and which is orchestrated by Panda. Okay, so let me just in the last 2 minutes, very, very quickly mention that QCD, lattice QCD is extremely important that touches all nuclear physics program, hard QCD, cold QCD, QCD in general, fundamental symmetry, nuclear structure, nuclear astrophysics. And just one example in the case of hard QCD, so the calculation, the graph shows a recent calculation of the heavy quark diffusion coefficient. But the bottom line is that we really need algorithm development, X-scale computing resources in order to meet the requirement of the hard QCD program. And in terms of hadronic structure, again, one will need we'll also need the algorithm development, X-scale computing resources, which is very, very important. So here, the subject area is also very, very rich in terms of the three-dimensional structure, and which has a lot of challenges in terms of doing a very precise calculation and handle the noise problems. And this is another example, and you can look in your leisure, it's all posted in terms of cold QCD, lattice QCD calculation on hadron spectroscopy, nuclear, and also test of fundamental symmetries. And near the end, I just want to mention X-scale computing project. Lattice QCD is a very important part of the ASCA project to help develop software application for X-scale machine at both ANL, Argonne, and also Oak Ridge. And lattice QCD is also one of the 11 applications selected to compose one of the key performance parameter of the project. So in closing, I just want to leave this slide here. David Dean and many others organized a computing nuclear physics AI/ML workshop last year. And this is the recommendation from that workshop. Thank you.
Any questions? I guess I see one hand over there. Far enough.
Hi, thank you for the talk. I was wondering if you could describe how U.S. leadership decided on these points for the long-range development plan as opposed to others. So what, or in other words, how was it decided that these were the priorities for the long-range development plan to make these developments as opposed to others? Thank you.
Actually, I didn't completely get your question. I'm sorry. Can you repeat?
In the long-range development plan, you outlined certain end deliverables at the end of it, right? You know, we hope to follow this trajectory for the development of science and for the development of software. How is it decided that these should be the goals as opposed to potentially other goals that we should focus on?
So, okay, so in terms of the long-range plan recommendation goals, as I mentioned, nuclear physics has been doing long-range plan for more than 40 years. So that I didn't show you what 2015 long-range plan recommended. And so every time we look, making sure that, you know, the recommendation of the previous long-range plan has been, you know, realized, or we are on a very good path to complete. And so what will happen after the all these town meeting is the entire long-range plan writing committee, which has a member of more than 60 people. And currently we are working on writing the long-range plan, but there will be a resolution meeting because I didn't show you, each town meeting has their recommendations and initiatives. And some of the recommendation initiative are connected to, related to computing. And so this more than 60 people committee will have 1 week in July, not very far from here, Virginia Beach. We will have a resolution meeting and we will debate, we will discuss, and we will listen, and we will argue. And of course, there is a reality, which is also budget, right? So there's a science and there's a budget. And then the community in the end is always able to come together to agree on a set of recommendations. And that recommendation will impact science, computing. I mean, computing is part of doing science.
Okay. I don't see any more hands. Thank you for the talk. Our next speaker is Jini Ramprakash. Got it right. Integrated Research Infrastructure Architecture and Blueprint. Okay, so we need to move to that one. Good to go.
Thank you. Hi, everyone. I understand I stand between you and exciting excursions, so I'll try to make this really quick. I know we're already behind on schedule. So as Randy mentioned, I work at Argonne National Lab, and I'm going to fly through these first introduction slides to get to the meat of the matter. Argonne has 5 of the 28 DOE user facilities, and these are the facilities that we house currently. If you're not familiar with it, Department of Energy has many scientific user facilities across the country, housed at various different national labs. And these are the 4 user facilities that are housed within the Advanced Scientific Computing Research Directorate at the Department of Energy Office of Science. And here's a little bit of an introduction into each one of these. There we have the Leadership Computing Facility at Argonne. We have the Leadership Computing Facility at Oak Ridge. We have the National Energy Research Scientific Computing Center, or NERSC, over at Berkeley, and the Energy Sciences Network, which is of course connecting campuses across the country and beyond. So this slide basically talks to the vision behind this integrated research infrastructure. And the idea here is not unfamiliar to a lot of people in this room. It is that, together we can do a lot more than we can do independently, right? So the idea is to be able to form an integrated infrastructure in such a way that the experimental and observational user facilities are connected to the computational user facilities, and we can combine their individual capabilities in such a way that we can do more than they can today. So that's the high level vision behind the integrated research infrastructure that's being talked about right now across the Office of Science offices. I believe it's been, so this slide is courtesy of Ben Brown at ASCR, and he has been the one that's been kind of pushing this initiative across the Office of Science offices. I don't remember if I have a slide with the HEP person who's engaged at the Office of Science or not, but as part of this vision, we did a whole bunch of activities in the past couple of years, starting back in 2020. And this is just a quick timeline of the key activities that have taken place so far around this concept of integrated research infrastructure. It started back in 2020 when ASCR launched this task force, and the task force got together and started talking about what does integrated research infrastructure even mean? What are some of the things that people have already done that move the needle towards such an infrastructure? The task force basically published a white paper that's out there, and I think it's in one of my future slides. It took about a year because pandemic time, we were meeting online, we were meeting somewhat regularly, but it took about a year for us to put out this first white paper. And the first white paper, these are the participants of that task force. And this white paper basically came out with these list of items that we thought we needed to emphasize in order to move forward with any kind of an integrated research infrastructure. So we talked about various aspects of an IRI and what those mean. And this is the list that was published as part of that, the initial task force work. Okay, so we had this task force and we came up with this white paper. What next? So one of the big findings of the task force was that across DOE, there are various different initiatives that have been working towards this kind of integration. A lot of them have been pairwise integration. Some of them have actually gone beyond pairwise integration across just 2 user facilities and gone on to multiple user facilities. But at the same time, they are all either lab level projects or partnerships through just proximity based partnerships, et cetera. And so this is, this slide has a list of a few of these. And diagrams of successful initiatives that have resulted in some kind of integration between multiple user facilities doing more than what they individually could. But the finding here is that these were all separate initiatives with very similar integration goals. And the idea of IRI is that let's now find a way to put all these under a single umbrella and move in the same direction. So the vision slide that I had was a high-level vision of what an integrated research infrastructure would be like. This is a little bit more of a, rubber meets the road. What would integrated research infrastructure take? And this is just, an example of, as you can see, APS, which is the Advanced Photon Source at Argonne, is kind of an example here. And the various different aspects that it would take to do this kind of integration between an experimental facility like APS and compute resources such as the ones that we have at ALCF. And the boxes highlighted here speak to some of the work that we have started doing towards this kind of integration. So we have, here I'm talking about the Argonne's initiative. We have put in network improvements that improve connectivity between our facilities. We've put in, we have multiple examples of workflow and orchestration tools that will help these individual user facilities orchestrate the work that needs to go across the facilities. And then we've done a bunch of work around both discoverable data repositories in our community data co-op, as well as what we would call experiment time on demand computing. And I know I saw this mentioned in this morning's plenary as well, where you're talking about offline versus near real time or experiment time computing work that needs to get done. So I know the community here has been discussing this as well. The next few slides go over some of the things that we've done at Argonne that helped move us towards integrating research infrastructure. So I'm going to fly through these slides in the interest of time. This one is, again, partnering with the APS. This one was partnering with the D3D Tokamak user facility, and this brings in our workflow and orchestration tool here that was used called Balsam. And you'll see that at the bottom of the slide is the reference to the actual work that was done and the paper that was published. This particular work done in 2019 crossed multiple user facilities. As you can see, this connected ALCF with the APS, as well as with ALS and NSLS2, all light sources in this case. But the idea here is to try and get it to a point where it was an experiment in the loop computing, and it was published at the workshop around large-scale experiment in the loop computing work. Okay, so coming back to the Integrated Research Infrastructure initiative that's coming out of ASCR, and the timeline that I presented to you before, after the white paper was published and after we established that we had all these separate initiatives, Ben Brown at ASCR decided to take the next step and pulled together a bunch of us and charged us with leading what he called the architecture blueprint activity. And this is the slide that has the people from the Office of Science offices that are also engaged with him in conversations within the Office of Science. So it looks like Jeremy Love and Eric Church are the HEP people in the leadership group there, and Jiafeng Gu and Jim Sawinski from nuclear physics. So I'm not sure if this community is already familiar with these names. But the idea here was that we would engage with all 28 user facilities and bring the people from the various different facilities together, and organize ourselves to be able to talk through the various different technological, policy, sociological challenges that we would face if we were to move forward with this idea of integrated research infrastructure. And we had over 150 people convene last year. Around this time, Amber and I were going around with our hair on fire, trying to organize all of it. But, 150 people, but we were 8 of us leading various different conversations. And some of the things that came out of those very useful conversations that we had was we figured that we needed a way to organize this. And the way that we ended up organizing it is by separating these out into science patterns and practice areas. Now, what do we mean by each one of these things? So a science pattern is like a broad class of workflows which have some common features. And for our purposes, we ended up putting together these 3 different science patterns, which was time-sensitive pattern, a data integration intensive pattern, and long-term campaign patterns, acknowledging that these are not mutually exclusive all the time. So there will be some overlap between these various different patterns, but the idea was we had to have some way of organizing ourselves and organizing the conversations, and this was one way in which we did this. And as the slide says, a given workflow could span several different science patterns, in addition to the science patterns themselves having overlaps. So, kept that in mind. The other aspect was these things we called practice areas, and these are cross-cutting communities of practice that span the various different science areas or the science patterns that were in the previous slide. So these were the list of practice areas that we came together and said we had to talk through and try and figure out. And as you can see, there's, starting with user experience to cybersecurity and beyond, we had 6 of these practice areas that we ended up having conversations around. So last year we had all these conversations. You saw the timeline that I presented. The architectural blueprint activity from last year resulted in a series of conversations around each of these practice areas and science patterns. And we are bringing all of this together into a summary guide. That's what we're calling it. And we expect to publish this final report and summary guide really soon, hopefully in the next month or so. And that will have all the, like a summary of all the conversations that were held around these various different areas that we talked about last year. I had this in my slides because this kind of speaks to the future. So in FY24, the president's budget request actually has language in there that talks about not just continue planning, but begin implementation to advance integrated research infrastructure. And this has been, this is something that's a big upside for the entire initiative. Of course, we all know that the president's budget request doesn't necessarily always translate to appropriations and all that fun stuff, but this is a good thing to have in the budget request, even if it doesn't end up getting funded. And then the other thing that has a lot of the integrated research infrastructure in there is this high performance data facility call that was announced earlier this year. And I think a lot of people might be familiar with it, but if not, then the call URL is on this slide here. So this is essentially my last slide, but I thought I'd leave with a few points about what's next with this integrated research infrastructure. Okay, so we have had these conversations with 150 different people from 28 different user facilities. It looks like we might be able to put this report out that has the synopsis of the various different conversations we had around the various different areas. The next set of steps at ASCR are trying to figure out early partnerships that we can have between user facilities and within the communities that those user facilities support to try and identify and move forward with initiatives that we can fold into the umbrella of integration and make progress on. So the next thing is steering and governance of this IRI program will be at the DOE Office of Science. And as I mentioned, ASCR has some kind of a leadership role, as well as the other Office of Science offices have people representing this steering body. And so we've got to figure out how we're going to steer an initiative like this. And the final one is we've started this idea of an IRI test bed. And as of now, it is not very well defined, but the next set of steps is to try and figure out what such a test bed might be, what it would take to make it useful to the community, to ourselves, and how to engage with the various different communities that we support, etc. So kind of leaving you with that. That's the end of my talk.
Any questions up the front? Where's the microphone? Coming.
Paolo Calafiora, Berkeley. Thanks for the great talk. So I guess when it comes to IRI, HEP is suffering a little bit from the innovator's dilemma because, you know, like 6 years ago, we started streaming data across the Atlantic when the CERN Computing Center was overwhelmed and processed raw data here. So I guess my question is, many lessons, many mistakes have been made. To which extent IRI is aware of these mistakes and these things? And to which extent, you know, we have so much production solutions for this. To which extent can we count on the fact that whatever IRI will produce, recommend, will take into account all this legacy, all this production work?
That's a fantastic question. So, you know, among all the conversations that we've had I see some of my colleagues who were involved in these IRI conversations in the room as well. So I'm, happy to have them chime in. Many of the conversations we had were also around the different places that each of the communities were at and what that means for each of them. So as you mentioned, HEP might have areas that they are well ahead of other Office of Science offices or other communities. And what does that mean for IRI? So the idea is that we pick up the lessons that we've learned through the experiences of communities that might be more mature than others, and we apply those across communities. So ASCR has one unique aspect of ASCR is that we engage across communities, and so we can actually see some of the lessons that we can apply across communities, or at least recommend across communities. And so the idea is to take those lessons and to apply them in whatever it is that we roll out to the broader across communities. Hopefully, of course, that's a challenge. It will be, because by the time we adopt that, you would probably move on, and there's a lot of sociological challenges, there's a lot of technological challenges there, but that's the idea.
Wait for you in the far corner.
Yeah, Maria Girone from CERN. So thanks for the very interesting talk. A number of the activities that you were covering, describing, are also happening in a way on the European side. And my question here is, how can we make sure that we are actually making a journey together from the communities and infrastructure perspective? This needs to be done, and needs to be done in a way that is coherent and done as much possible together. And that's not an easy thing. So what's your...
True. Yeah, so thank you for that question. That's a very valid point. So even as we were having these conversations, our leadership group were having our own conversations around how our colleagues in Europe were doing we're doing very similar things. And I had suggested some of our colleagues over in Europe who are doing similar things come and talk to us about what they were doing, and us going and talking to them about what we're doing, so that we can learn from each other, and that our communities are across the world. Obviously, they're not limited to just the continental US or even just US and Europe. So it's going to be important to do that. At the same time, the connections that we have between facilities, though, is going to suffer from the geopolitical boundaries of their funding. So there's a line to walk, but I would love to connect and see where we go.
There was one more question here.
Okay, so I think idea of IRI is great, but still, to some people would consider as some kind of like a exclusive playground for the elite, for the rich, in some sense. Let's a little bit like a very simple thought term. Can you make it even broader? For example, instead of integrated ISI, let's call it OSI, open science infrastructure or whatever. And for example, you can open the facility to broadly, to the general citizen, to high school, to college. And then even further, can be open, for example, build the facilities not only for the center of instruments. Let's integrate things, for example, from the traffic system, from all kind of large scale instruments, essentially Internet of Things, large scale sensors, sort of make it very, very broad. Then therefore the society says, oh, that's now the only playground, which is a cost center, at least in the short term, can become some way of general citizen service. I know that's probably too complex, but just throw it out as potential proposal.
But that's the vision. I completely understand you're saying it's complex, but it's always great to work towards a vision that has that kind of it's a utopian world where everything is connected and anything can talk to anybody. We also spent a lot of time talking about what levels of, so in my case, compute, right? What different levels of compute we need to talk about integrating with experiments, starting from the desktop, starting from the end station work the workstation at the end station at any experiment, all the way up to the supercomputer, every step and, campus clusters, like all of them come into play here. The idea is fantastic. The implementation is where everything comes to a screeching halt. So as of now, this is the vision, is to focus on these user facilities. Hopefully that will include more and more in the future.
Okay, well, let's thank Jini again. Yeah.
Okay, just one quick announcement, and that is if you have been expecting an email about your excursion and you haven't gotten it, please proceed with all haste up to the 3rd floor and talk to the people at the registration desk. Hopefully nobody's in that situation.